So today we're doing exploratory data analysis, which basically means you don't go in with a hypothesis, you just kind of get your set of data and you want to take a look and see what's there. It's generally the first step that you're going to do, actually, is like get your data set and just kind of look around and see what's going on with it. But to do that, we need some of the statistics for the statistical part of the analysis that we've done so far. So that's why, even though this is the first step, we're just doing it now in the semester. So we're going to do it in a couple ways, both statistically and doing some visualizations for exploratory analysis. I actually think visualizations are a great way to start, and I tend to do visualizations first and then do the statistics. But we're going to start with the statistics because we're going to spend more time on the visualization, so it'll let us kind of extend that out. So to do exploratory data analysis with statistics, you're generally going to be looking at correlations. In the notes for today, you'll see I have this cherry data part 2. This is cherry blossom bloom data. So let's go ahead and download that. And for now, we'll just take a look at it to see what's there. So what we have is cherry blossom bloom data from every year starting in 1921. We have the day that they actually reached peak bloom. And so that's the days from when we started looking, from when they kind of start the process, the date of the peak bloom. And then we have temperatures in January, February, and March, whether or not there was snow. This is measured in inches, how many inches of snow were there in January, February, and March. The date of the last frost, or how many days in was the day of the last frost. And then we have these two variables, green buds and florets visible. And there's 5 distinct stages that they go through. So these are 2 of those stages. Green buds start popping out on the branches, and then the floret is visible. It's where you can kind of see like the little flower bud on there. These are blank. This data only starts down here in 2004. Okay, so we have that data from 2004 through 2015. Every year on here has a peak bloom date back to 1921. Let's just take a look down at this data. So here we have days for green buds, florets visible, and then this column over here is when they actually reached peak bloom. Okay, these are day numbers. So day 64, day 72, day 91. And we want to kind of explore this data and figure out, is there a relationship between things like when the green buds start and when there's peak bloom? Do you think there is? Is there a relationship between those things? Like logically. Yes, there should be, right? Like when they start the process of blooming should be related to when they actually do the blooming, right? So we're going to look at how to go through this in R. But first I just want to talk about how we might actually compute that. Is there a relationship between those things? So we have kind of 3 things that we're looking at here. So the green buds are visible, the florets are visible, and then peak bloom. Okay, so those are our 3 data points. And we may want to see what's the relationship, say, does the day that the green buds come out relate to when the peak bloom is? Or did the day that the florets come out relate to when the peak bloom is, right? Those are the questions. We just want to explore, is there a relationship there or not? So one way that you can do this is with a correlation. If we were to plot this, we may put the green buds down here and then just actually have our days. And the peak bloom over here and have our days. And then you'll plot them. And once we get all of our dots plotted, then we draw a line through this that's going to be a best fit. So it might look something like this. The later the green buds are, the later the peak bloom is. That would suggest. And the slope of this line is the correlation. Positive slope line, positive correlation. Flat line is a no correlation. This line is a negative correlation. And covariance is just exactly what the name sounds like. If you have 2 variables, how do they vary with each other? So if one goes up, does the other one go up? If one goes down, does the other one go down? Do they vary together? What's their covariance? And so we compute that. You'll never have to do this by hand, so I'm kind of showing you the formulas, but we're going to always do this in R. You'll not have to reproduce these formulas. So you take your observation of the first variable minus the mean. times your observation for the second variable minus its mean, and you sum all of that up over n minus 1. That's going to give you the covariance. We'll do this in R in a minute. The Pearson correlation is just the covariance of x and y divided by the standard deviation of x times the standard deviation of y. That's going to give us this Pearson correlation. It takes the covariance, this essentially normalizes it, and it's going to put it on that -1 to +1 scale for us. So let's actually try this in R. So I'm here in RStudio. We want to load up that file. So I'll call it cherry. And we're going to do read.csv, file.choose to open that file, and header equals true. All right, so then I'll pick my cherry blossom data there. And it's loaded up. We have 95 observations. That's the 95 years that we have data for. Now, we can just compute the correlation, but I want to kind of walk us through the process of how this works with covariance and the kind of derivation of it first, just so you can kind of see that. So we can try to do covariance. The command for that is COV for covariance. So we can do cov.test, and then just give it the two values that, the two variables that we want to check how they covary, how do they move together. So we could do cherry $, green buds, so when did the buds first become visible, and cherry $, the day of the peak bloom, but that's not going to work. Oh, what did I do wrong? Oh, so it's just, I'm sorry, that's just COV. There we go. I expected an error, just a different one. So not COV.test, just COV. So the covariance, it just gives us an NA, right? If you get an NA in R, that means you have blank data, usually is what that means. And of course we do, right? When we were looking at this in Excel, we have all of these, everything before 2004, we don't have any data for the green buds, and so it can't do the covariance for us. The correlation actually is able to overlook that, and it just computes it with the data it has. But for covariance, we need to actually take a subset. So let's create a data set called C2, because we have cherries, so this will be C for cherries number 2. And that is going to be, remember this command, na.omit. That's going to get rid of any rows that have blank data in them. So we're going to do na.omit for our cherry data set, and that will get rid of all those rows that don't have any of the green bud data. So we're going to keep the original cherry data set and just make this subset. So once we do that, over here in the environment, you can see we have now 12 observations. That's the 12 years that we have the green bud and the floret data visible for. So now we can do the same thing, the covariance, but we'll do C2 $ green buds and C2 $ the day of the peak bloom, and then we get our covariance. Okay, I'm going to do the same thing. I'm just going to store that in a variable, so I'll do like CV for covariance. It's going to store that for us, but you can type it back in later if you want to. All right, so to get the correlation, we take the covariance divided by the standard deviation of x times the standard deviation of y. So we can say CV over SD for standard deviation of C2 $ green buds. So that's going to give us the standard deviation of our first variable times the standard deviation of the day of the peak bloom. Make sure all my parentheses match there. If it's easier for you, like when I did this the first time, I actually created like a variable for the standard deviation of x and another one for the standard deviation of y, so it wasn't this parenthetical mess up here. It's up to you however you want to do that. All right, so what we should end up with is this value, 0.738. That's our Pearson correlation coefficient. And that's on this scale, -1 to +1. Okay, so how do we interpret that? Generally, we have a similar kind of scale that we had when we were looking at effect size. Roughly, if you have a correlation of like 0.3, sometimes we'll go down to 0.2. We would say that's a sort of weak correlation. Something of like 0.5 would be medium. Something of like 0.7 would be strong. Okay, so here we did this whole process, starting with covariance, but you can actually just do a correlation test directly in R. So to do that, we do, let me, this up here, core.test. So we're going to do a correlation test, and we can just put in our two variables there. So C2 green buds, C2 day of peak bloom, and it prints out this whole little report for us for the correlation test. The thing to look at is at the very bottom, it tells us what the actual correlation is, which is what we just computed, right? That's the same value that we just got when we did it by computing the covariance dividing by the standard deviations of the two variables. So this will also work even on our original data set that has the blanks, because when you're computing correlations, it just ignores blank values. So you could do the same thing with the cherry data set instead of C2, and it would give you the right answer. It wouldn't give you the NA. What this also gives you, though, is a test of the significance of your correlation. And just like if we're reporting differences in the mean, we want to say if it's statistically significant. Here, if you're reporting a correlation, you want to say if it's statistically significant, too. And so this gives you a p-value. It's the same as the p-values we've been doing. In fact, this is essentially, there's a t-test underlying this. Degrees of freedom, a p-value, and we interpret this exactly like we have. So if your p-value is less than 0.05, you can say there's a significant correlation between the two values.